Okay, so 7.4 is all about vectors. In terms of math, you will deal with vectors if you continue on in your mathematical career and take Calc 2. That is really the first place you are really going to play around with vectors a whole lot. That's basically all Calc 2 is vectors. If you take a physics class, you will deal with vectors. So it's definitely something that comes up in other classes, not just trig. It's meant to kind of be an introduction here, so that at least you've heard of vectors, you've maybe seen vectors. We're going to do a couple of problems with vectors, but this is definitely not an exhaustive exposure to vectors. So just know that this is meant to be a broad stroke situation where we're kind of just getting you comfortable with some of the terminology. So as you can see on the handout, there is a lot of terminology. The first one is scalars. Scalars are quantities including magnitudes, involving magnitudes that are represented by real numbers. We've heard scalars before. That is a common terminology that you use in math. You did scalar multiplication in college algebra when it came to matrices, and that's really where you just have a coefficient out in front of your matrix that you apply, and that's pretty much what a scalar does here. You can have scalars in terms of your vectors. So scalars involve magnitudes. Then you have your vector quantities that involve both magnitude and direction. So the common types of vector quantities that you're going to learn about in like physics and stuff like that would be velocities or acceleration or force. 50 miles per hour east is a vector quantity because you have the 50 miles per hour, which is the magnitude, and you have a direction, which is east. So that is what a vector quantity is. If you've ever seen Despicable Me, the very first one, the villain's name is Vector, and he talks about how he chose that name because he has magnitude and direction, and he's a big dork. And this is where he got it from. He got it from mathematics. And so his name does mathematically hold up. So if you haven't seen that in a while, there's your homework assignment for the weekend. Go watch Despicable Me. It'll make you happy. Vectors are a directed line segment that represents a vector quantity. A lot of times we talk about vector quantities, but we just really say vectors. They are different, but in all reality, if you're talking about a vector, you're meaning a vector quantity. In a textbook, vectors can be represented just as bold type, which is hard to represent in notes. And so we have the little line segment with the arrow like that over your starting and your terminal, your initial point and your terminal point. This is a vector. So it looks very much like in geometry a line segment or a ray. But it is important the order of your points and the direction of your ray or your vector. In general, we always have the vector going from left to right, and what we will end up doing is changing the order of the letters around, not necessarily switching like where we leave it as OP and going this way. There's nothing wrong with this, but in general we usually have the arrow headed to the right. The magnitude, when you are talking about a vector, is represented by the length of the vector ray or the vector line segment. And so the longer the vector, the greater the magnitude. The shorter the vector, the shorter the magnitude. Initial point versus terminal point. If we look at the vector OP, then it starts at the initial point O and it ends at the terminal point P. If we look at the vector PO, we're starting at P and we're ending at O. So the order matters a lot. Both of these vectors have the same magnitude, but they actually represent different vectors because they are headed in opposite directions. So order matters a lot when you talk about vectors. Two vectors are considered equal if and only if they have the exact same magnitude and the exact same direction. So the reason why OP and PO are not considered the same is because they head off in opposite directions. So here we have a couple of vectors. We have A, B, C, D, and E, and F. What vectors are the same? Which ones have the same direction and magnitude? Or let's just start with A. Is there any vector that is equal to A? B. Is there any others? No. Okay, that is correct. These are the only two that have the same length that are headed in the same direction. Okay, what about C? D. And maybe we can make an argument that E, but E looks like it's tilted slightly different. I feel like the point is that C and D are. And even though A, B, C, and D all have the same magnitude, because they head in different directions, we can't say that all four of those vectors are the same. What can we say about E and F? Are those the same? No. They head in totally different directions. F is noticeably shorter than all of our other vectors, so they're not equal. Some of your homework problems or quiz questions literally look at a pile of vectors and you tell me which ones are the same. I'm not trying to make it hard here at the end. All right. Let's look at the sum of two vectors. So we're going to add our vectors together. There's two different ways we can do this. We can do it with a triangle. We can do it with a parallelogram. It's important to note that two vectors, if you add them together, you will still get a vector. Vector addition is commutative. That means that A plus B is the same thing as B plus A. So that's kind of nice. The first way that we can solve vector addition is by using the triangle method, and that is where you place the initial point of vector B. So the initial point is your starting point. So you place that at the terminal point of A. So basically you go starting, terminal, starting, terminal. The vector with the same initial point as A and the same terminal point as B is the sum vector. So you always want the opposite sides to go together is basically what happens when you're using the triangle method in terms of the two that they give you. That's great. I will be honest, the way that we're going to probably approach most of these is using the parallelogram method, which is the next one. And that's where we place both vectors A and B with their starting or their initial points together, like in the corner, and we have them headed in opposite directions. Then we use dashed lines to complete our parallelogram because by rules of parallelograms, the opposite sides are always the same length. The most common parallelogram that you are used to playing around with is your rectangle. And think about it, you have long sides and short sides. The long sides have the same measure, the short sides have the same measure. Same thing is true here with our vectors. The diagonal of the parallelogram is going to go from the initial point over to this corner. And just like up here, that diagonal is going to be that sum of the two vectors. So all of them that I do with you today are going to use the parallelogram rule. If you prefer using just the regular triangle, you totally can. Okay, we're not going to get super picky on this. All right, let's flip it over so we can remind ourselves a little bit about some of our general properties of parallelograms since we are going to play around with them. A parallelogram is a quadrilateral, that means four-sided polygon, whose opposite sides are parallel, thus the name parallelogram. The opposite sides and opposite angles of a parallelogram are equal. So opposite sides, going back to the front so that we can see a general picture, that means that this side is equal and this side is equal. They're opposite, but it also said the opposite angles. So that means this angle over here would have the same measure as this angle over here. And this angle up here would have the same measure as this angle down here. That's what they're saying. And adjacent angles of a parallelogram are supplementary. If you have supplementary angles, what does that mean? Yeah, they equal 180. So that means the measure of angle star and the measure of angle box have to equal 180. You can call them whatever you want. So that's important. So if these two adjacent angles equal 180 degrees, what do we know about all of the angles inside of our parallelogram? Right. So all interior angles of our parallelogram add up to 360. So that's important to note. Okay, and the last of our properties state that the diagonals of parallelograms bisect each other, but they do not necessarily bisect the angles of the parallelogram. Cool. Not a lot there. So let's look at a physics problem, kind of, not really. There was some legit physics problems, so if physics is your thing, this chapter, this section, 7.4, there's a lot of really good examples about pulling things up inclines. And if you like doing problems where we pull big boxes up inclines or we send them shooting down ramps, this is what you're using vectors for. I did some more generalized, more mathy problems instead of physics problems, because this is a math class, not a physics class. If you want to take physics, you can go take physics. So it says two forces of 15 and 22 newtons act on a point in a plane. A newton is a unit of force that equals 0.225 pounds. If the angle between the forces is 100 degrees, let's find the magnitude of that resultant force. Okay, that's a lot of stuff, and it's a lot of physicsy stuff. So here's what I'm going to do. I am going to treat this like a parallelogram. And so our parallelograms, what we do is we put our two vectors where the initial sides start at the same point. Okay? And it says that we have a force of 15 and a force of 22 newtons. So we have 15, we have 22. I have them starting at the exact same point, and I angled it this far out because it tells me that my angle between them is about 100 degrees. So it's not going to be perfectly perpendicular up and down because that's 90. We got to go about 10 degrees further and thus have this obtuse angle. So if I'm going to make a parallelogram, I'm going to draw some dashed lines to get a generalized picture of my parallelogram. It's not the best. It's kind of wonky. But you will never be judged on your artistry in this class. So if we're doing a sum situation, what we get is here. And they label it with a V, and so I'm going to label it with a V. You wouldn't know that because you haven't seen an example yet, so now you know that we label it with a V. We need to come up with what is the magnitude of the force that heads off in this direction. And you're like, okay, great. I have no idea how we do that. Well, actually you do. You just don't realize it just yet. If I'm looking at what I have right now, I have a side, I have an angle, and I have a side. What did we use for that? Or what have we learned about in Chapter 7 so far? We've done law of sines. We've done interior angles add up to 180, in triangle at least. And we've done law of cosines, right? Okay. What did we use law of cosines for? Because that was a smaller list. And that was the most recent stuff we learned. It was side, side, side. And what else? Huh? Yeah, we did some ambiguous. That was 7.2. We used law of sines for that, though. What did we do on Monday? Side angle side. So if we have side angle side, that's telling us we're going to use law of cosines. let me give you a hint. You're going to use law of cosines on all of these. I guess that's a spoiler alert. Because what we have is we have this side, and we have this angle that results between them. But the problem is that the side we're trying to come up with runs right in the middle of this angle, right? So that's kind of a problem. But if we know that this angle is 100, that means this angle is 100. And we know that all the angles inside have to add up to 360. So how much is this angle over here? 80, that's right. This is 80. Notice that this angle, my 80-degree angle, lies across from the side that I'm trying to figure out. And that's what we need in order to do our law of cosines. Because with our law of cosines, if you remember, we have a squared, or whatever letter you want it to be, because it changes depending on which side you have. But we have a squared equals b squared plus c squared minus 2bc cosine A, where we're always trying to find the side that is opposite of the angle that we have. Well, we have this 80 that's across from this side that we don't know. We know the other two sides because you can write 22 over here if that makes you more comfortable. So one of these is B, one of these is C. This V is what we're trying to solve for. That's our little a. Are we tracking this? Slightly. Okay, so I'm going to write A next to that V so you see where it is. So we have 15 squared plus 22 squared minus 2 times 15 times 22 times cosine of 80. We're going to round to the nearest Newton, so the whole number. And whoever gets it first can yell it at me. Oh, wow, you're fast. Okay. Yeah, 24 newtons. So for these problems, they're all going to work very similarly, all of them. Where you're going to draw your parallelogram, you're going to draw your diagonal. You do need to figure out the rest of your interior angles, and then you're going to apply your law of cosines in order to figure out the distance of that diagonal. Are there questions on this one? Questions on how I drew it, how I got what I got, where I got it, any of that? Okay. These bottom two are literally the same thing, they're just not word problems. It says use the parallelogram rule to find the magnitude of the resultant force of the two forces shown in the figure. Round your answers to the nearest tenth. So it does tell you to round to the nearest tenth. If we're using the parallelogram rule, we're going to finish our parallelograms. And we draw our diagonal in. And that diagonal is what we're trying to find, because that diagonal is equal to the magnitudes of the other two sides. So this is always what we're going to be looking for, is the diagonal. Now, if this bottom angle is 40, that means this top angle is 40. So what are these big obtuse angles? 140. We have to find out what that obtuse angle is, or the one that's opposite of our diagonal in this case, because that's the one that we have to take the cosine of. Oh, don't do that. We'll have 40 squared plus 60 squared minus 2 times 40 times 60 cosine 140. And we find that our resultant force is how much? Round to the nearest tenth. That's one decimal place. 94.2. And usually whatever label they use is the label that you'll use. I mean, you don't ever have to type those in because those are just included in the answers. Like, you just have to type in the numbers. But these are plug and chugs. What is the measure of the angle in our second one? Down here. Huh? Remember, the adjacent angle, so this angle that they give me and the angle over here have to add up to 180. So how much is the angle we don't know? 70. Because they're supplementary. So this one I have v squared equals 15 squared plus 25 squared minus 2 times 15 times 25 cosine of 70. So how much is my resultant force on this one? $24.4. And remember from our, I think it was the last section, we had the rule about the measure of the sides of our triangles and how two sides, if we add them together, should always be greater than the last side. And because we still are having triangles here, even inside of our parallelograms, I mean, that still holds. If I have a side of 60 and a side of 40, then my resultant vector had better be less than 100. And it is. It's 94.2. Or down here, my resultant vector had better be less than 40, which it is. And so you can kind of do a quick check, not on that it's right, but at least that it still holds with your triangle side information that you do know from 7.3.